And there's the bottom of the page, just in case anyone was wondering. Oh, look, it's highlighted in cyan rather than pink, so there is a difference. There are all kinds of calculations going on this thing. You input, you can input the Earth's polar radius and equatorial radius if you really want to. You put in the refraction numerator and denominator, although for this I didn't need to bother. To set them wherever you like, Obviously, you have to put in an observer latitude and longitude and altitude so that it knows where you are, and the camera azimuth and elevation angle so it knows which way you're looking for it to be able to predict what you're going to see. Observer sea level radius is calculated based on a formula copied off online.de. Refracted sea level radius is then calculated just based on the refraction thing. The upper one is multiplied by the refraction numerator divided by refraction denominator. The two below it just multiplied by 1.1 and multiplied by 1.25. Sea level, and then the actual radius is that sea level radius plus the observer altitude that you input. Actual X, Y, and Z, which may not necessarily match the X, Y, and Z of GPS systems, because I may have come up with my own X, Y, and Z for this. Maybe they do, maybe they don't. Negative, and positive does match what you would get on GPS, but the magnitudes might be a little out. Farther negative X than negative Y suggests I have the X and Y the other way around than the GPS system has it. Anyway, you input target latitude, longitude, and altitude. It converts those to radians, because a lot of things work in radians. And it works out the target's sea level radius, actual and refracted sea level radius, and radius including altitude, and refracted radius including altitude, just as if the observer, and works out the mean refracted sea level, which is an average of the two positions, because it's going to need that for calculations later. Then it gets actual X, Y, and Z for the target, breaks down, compares that to the observer's X, Y, and Z to get a vector, rotates that to get vector B. Vector A is just direct. Vector B is, I forget which one, I think it was rotated longitude first, then latitude first. Vector C is relative to north, east, and up at the observer's location. And from vector C, you can it calculates vector C azimuth, which is the direction from the observer to the target. Vector C distance is the actual straight line distance to the target. Vector C elevation is the elevation angle relative to observer location, relative to horizontal. Over on the right, refracted vector Y is, actually looking really weird now that I look at it. Refracted vector Y, 1.84, 1.833, 1.85. Oh no, it's alright, never mind. That looks fine. It doesn't include the geometric, it includes the 1150 over 1000 from cells C2 and D2 up there. To give you, refracted vector elevation, which is how far, refracted vector Y is the vertical shift. Just kind of, yeah, I don't know which way around X, Y, and Z were when I set this thing up, but it does seem to work. Refracted vector Y is the vertical shift to the target. Refracted vector elevation is the angle to the target. The elevation angle of that target from the observer after that much refraction. The inputted amount of refraction, 1.1 hour refraction, 1.25 hour refraction. Azimuth relative to the camera is really simple. It's the vector C azimuth minus the camera azimuth, cell H3 up in the top right. elevation angle relative to the camera is the one in the bottom left is geometric. There's no refraction accounted for. You take the elevation angle that was worked out as vector C elevation and subtract the camera's elevation angle. Over on the right, refracted elevation relative to camera is the refracted vector elevation from above that minus the camera elevation angle. One thing I found using this before is that it's actually easier to set the camera up pointing above and to the left of all your targets so that all of your angles are positive numbers and you can simply go direct to GIMP rather than mucking around with whether it's positive or negative. But in this case, I have pointed the camera roughly down the middle of where I think the field of view was and exactly level. Camera elevation angle is 0. And there's the output in the bottom. X coordinate in view it's just the tangent of the azimuth relative to camera. Y coordinate in view geometric is the tangent of the elevation relative to camera. Y coordinate in view refracted is the tangent of one of those angles on the right. Notice they're very similar numbers because they are very small angles, and the tangent of a very small angle in radians is very similar to the angle itself in radians. Y coordinate view flat is worked out differently. This is where the distance and the change in elevation come in. It is the it is the tangent of the angle whose tangent is vector C elevation over vector C distance, or something like that. The change in altitude at that over the calculated actual distance to target. And of course, all I get repeated up the top right so that I don't have to scroll up and down all the time while I'm doing this. Example output, having actually put in Bobby Shaftow's location and observer altitude 4 meters because that's what Google Earth said. Camera azimuth 31 degrees because that's which way he was looking. Camera elevation angle 0 because leveled. Eye level is here in one of his later videos. And actual latitude, longitude and altitude for one of the targets. You have actual outputs here. X coordinate in view 0.06, there's an awful lot of 0.0 in this. 0.0682. Y coordinate in the view geometric, negative, meaning below eye level, 0.000499966, also known as 0.0005. Y coordinate view refracted, we've got various numbers that are all positive. So with refraction, that target is slightly above eye level. And this is a mountaintop. You'd hope it would be above eye level. But apparently it's below with curve, without refraction, just tiny bit below eye level. All small numbers. Y coordinate view flat, where all the refracted ones are 0.000 something, or 0.001 something. Without curvature or refraction, it's 0.0157, which is a whole lot higher up. It's just one example target. Different target. This is a point at sea level. It may well be part of the Point Robinson coastline. The X coordinate is now negative, so that's left of centre. The Y coordinate is below eye level, which you would expect the sea to be. And all the geometric and refracted coordinates are below eye level as well. From these, we can get an idea of how big the image needs to be. You can see, we can ignore the first 2 digits, but we're going to be mucking around with, well, you can ignore the 0 point, but you can see there's a 0.1 to the left there, so maybe we use the first 4 of the decimal places, and we make our image 2,000 pixels wide and 1,000 pixels high. So I started like that.